Bien, ahora sí, oficialmente muy buenos días, chicos, chicas, damas y caballeros. Esperamos que se encuentren bastante bien la mañana de este viernes. Para nosotros es un placer recibirles en este auditorio OCES en nombre del Instituto Tecnológico de Santo Domingo, donde hoy se llevará a cabo la conferencia Nuclear Energy, Does It Make Sense for the Dominican Republic?, a cargo del destacado experto Jacopo Buongiorno. Esta representa una excelente iniciativa para abordar un tema de gran relevancia para el futuro energético de nuestro país. La energía nuclear, aunque es una opción debatida a nivel mundial, ha demostrado su potencial en términos de eficiencia y sostenibilidad. En un contexto donde los países están buscando alternativas para enfrentar los desafíos del cambio climático y la creciente demanda de energía, es esencial preguntarnos si esta pues sería una solución para la República Dominicana. Permítanme saludar a las autoridades del INTEC que nos acompañan. Entre nosotros se encuentra el ingeniero Cayetano Rodríguez, decano del área de ingenierías. También nos acompaña Chahira Nasir, decana de Economía y Negocios. Igualmente saludamos al doctor Carlos Sanjay, director de investigación. Entre nosotros está también el señor Manuel Cabral, vicepresidente de Ingeniería de la Asociación Dominicana de Industrias Eléctricas. Saludamos igualmente a los coordinadores y docentes del área de ingenierías de nuestra universidad, así como a los estudiantes y pues a los representantes de los comités estudiantiles, quienes gentilmente se han sumado a esta conferencia. A quienes nos sintonizan a través de nuestro canal de YouTube, pues esta conferencia está siendo grabada para quienes desde manera virtual también quieren seguir ampliando el conocimiento y pues ser parte, gracias a informaciones como esta, iniciativas de los debates que se lleven a cabo. Por supuesto, y no menos importante, saludamos a nuestro invitado de honor y conferencista, para quien voy a pedir un fuerte aplauso, el señor Jacopo Buongiorno. Bien, como esto es un poco friendo y comiendo, quiero llamar adelante al que un poco estuvo a cargo de también llevar esta iniciativa y proponerla para que se diera a cabo esta mañana, Cayetano Rodríguez, el decano del área de ingenierías, quien va a tener unas breves palabras de bienvenida y también tendrá el honor de presentar y dar el paso pues a nuestro orador invitado, Jacopo Buongiorno. Con un aplauso le recibimos a nuestro decano.
Muchas gracias por la introducción. Sean todos bienvenidos y quiero sumar a las salutaciones a mi jefa ya atrás sentada, la casi ingeniera Priscila Castro, y al grupo de personas que ayudaron a organizar esto, y entonces ahí calladita está Priscila. Ven para acá adelante, ven con la... Bueno, no voy a invertir mucho tiempo en hacer muchas introducciones ni nada de eso. Solamente quiero leerles una breve reseña de la vida del profesor Buongiorno aquí, quien es profesor asociado de Ciencias e Ingeniería Nuclear en el Instituto Tecnológico de Massachusetts, MIT. La han oído mencionar, ¿verdad? MIT. ¿Le suena? Sí, como que hacen ingeniería ahí, ¿verdad? Con un doctorado en Ingeniería Nuclear de la misma universidad y una licenciatura del Politécnico de Milán. Sus áreas de especialización incluyen la tecnología de nanofluidos, dinámica de fluidos, transferencia de calor y flujo bifásico en sistemas nucleares avanzados. Ha recibido varios premios por su labor académica y de investigación, como el Landis Jones Member Engineering Achievement Award y el Ruth and Joel Spear Award for Distinguished Teaching en 2011. El profesor Buongiorno es miembro de la Sociedad Nuclear Americana, la ANS, y la Sociedad Americana de Ingenieros Mecánicos, la ASME, sociedad que, si ustedes son de ingeniería, que supongo que sí, habrán escuchado de esa asociación. Y ambas, la ASME y la ANS, son parte de la zapata de AIBET. ¿Le suena AIBET? Bueno, pues estas son 2 de las 35 asociaciones de ingeniería a nivel mundial que apoyan y que soportan la acreditadora de AIBET. Y codirige un curso sobre tecnología de reactores nucleares para ejecutivos. Además, es consultor en termohidráulica de reactores y participa en comités especializados, incluyendo el Comité Especial de la ANS sobre Fukushima. Sin más preámbulo, lo dejo entonces ahora con el profesor Buongiorno, a quien pido un fuerte aplauso.
All right. Good morning, and thank you for the introduction. I wish I could give this presentation in Spanish, but alas, I don't speak it, so you'll have to bear with me in English. They were very kind to give me until 11, which is at this point an hour and 25 minutes. But I think I'd like to leave ample time for the Q&A, questions and answers. So I'll try to keep the presentation here to a minimum. And I've changed the title a little bit. I think in the introduction you said I'm going to talk about nuclear energy. Does it make sense for the Dominican Republic? I may touch upon that aspect at the end, but I thought since we are at a school here, and I've noticed that you have the atomic symbol in your flag, that we would spend a little bit of time covering the basics of nuclear energy. What is nuclear energy? How does a nuclear reactor work? And all of that. And then at the end, we may get into the question of, is it a technology that makes sense for the DR or not? Does everybody follow, either in English or with the translation? Fantastic. Now, I like this to keep interactive, so feel free to raise your hand and ask me questions as we go. All right. Let's start with something very, very basic. Where does electricity come from? It is not a primary energy source. It's not something that we mine, as we may mine coal or natural gas or uranium. It's not something that we harvest, all right? So electricity is generated in machines that we call power plants from other primary energy sources. And so examples of primary energy sources could include coal, oil, natural gas, hydro, wind, solar, geothermal, and nuclear. Now, how does a power plant work? Well, there are many different designs and many different sort of approaches, but in the simplest approach, you have some kind of a heat source. This could be due to the combustion of coal, or it could be due to nuclear fission, which I'm about to describe. And you use that heat to produce some steam. And then you pass steam through a turbo generator, through a turbine, which through the laws of electromagnetism generates electrical work or electricity. So electrons start to flow in a conductor. And so then you sell your electricity to the grid. Now, to close this cycle, you take the steam that comes out of the turbine, which is now a relatively low temperature and pressure, and you condense it. You turn it back into water, into liquid water, and you pump it back to your heat source. So that's a fairly generic description of what a power plant might look like. Okay, so then what is nuclear power? Well, it's the generation of electricity by a nuclear reactor. Now, what is a nuclear reactor? Okay, so it's a system or a machine that realizes a self-sustained, stable nuclear fission chain reaction. This is a lot of words. I don't particularly like this slide, too many words. But now I'm going to tell you, I'm going to describe a little bit better what I mean by a self-sustained, stable nuclear fission chain reaction. Okay, so this goes back to basic physics. Again, very, very elementary. You guys are all scientists and engineers, so you know what the world is made of, atoms and nuclei. Within the atoms, you have a very, very sort of massive but very small, high-dense nucleus. Within the nucleus, you have protons and neutrons. And so the Z number, which is the atomic number, determines basically the elements. So Z equal 1 is hydrogen. Z equal 92, for example, is uranium. two nuclei with the same Z, with the same number of protons, if you will, but different number of neutrons are called isotopes, all right? And so for uranium, which is a material that we care a great deal about because it's the fuel that we use in nuclear reactors, there are two isotopes of interest, uranium-238 and uranium-235. So keep that in mind, please. Now, the first concept is chemical reactions. When you think about the combustion of something like natural gas or methane, breaks bonds at the atomic scale. So it involves the exchange of electrons between different atoms. Those are chemical reactions. Nuclear reactions break bonds at the nuclear scale. So it involves the exchange or transformation of neutrons and protons within the atomic nucleus. Okay? And the energy scales for chemical reactions and nuclear reactions are vastly different, millions of times different. This is going to be important, as we'll see, in terms of what a nuclear reactor does and how it works. Okay, so let's get to fission. So the starting point for the fission reaction is a nucleus of that uranium-235 isotope. If that nucleus absorbs a neutron coming from the outside, then more often than not, it splits into two halves. That's the process that we call fission. So it splits here into two fission fragments. Those are two lighter nuclei that come out of this reaction. Very importantly, this process liberates a lot of energy, which is going to be in the form of kinetic energy of these fission fragments going around. And also very importantly, as you see here, this reaction liberates two or more additional neutrons. Why is that important? That's the interactive part, so someone can answer. Why is it important that this reaction also generates additional neutrons? Because I can then create a chain reaction. If those neutrons find new nuclei of uranium-235, then I can have additional fission, you can see here, and then additional fission, and it goes on and on and on. Now, if I allow this reaction to take place very rapidly and divergingly, I do not have a nuclear reactor. I have an explosion. I have a nuclear weapon. But it turns out that it's actually very straightforward to control this reaction, to make it happen such that the rate at which fission takes place is constant. And so then it becomes nice and stable. So then what do I have? I have a constant source of heat, because the kinetic energy of those fission fragments is quickly converted to internal energy, or if you wish, thermal energy of the fuel itself. So fission essentially is a heat source, just like the combustion of coal or natural gas are heat sources. Okay? Now, that fuel is uranium-235, that isotope. Is it rare? Is it common? Well, unfortunately, it's not very common. Only 0.7% of natural uranium, uranium is a material that we mine from mines, as I'll explain in a few minutes. Only less than 1%, 0.7% is uranium-235. That's the material that we care about. The rest is uranium-238, which is, to a first approximation, fairly useless. Okay, so again, keep that in mind. All right, so this is where we keep it interactive. So there are going to be a few little quizzes here and there. Right? So let's read this together. How does the fission chain reaction in a nuclear reactor differ from the fission chain reaction in a nuclear weapon? I just explained it. So let's see. It does not involve neutrons. Is that true or not? In both cases, you got neutrons flying around. Otherwise, you don't have a chain reaction. It does not require fuel. Nope, you need fuel. You need that uranium-235 in both cases. The number of fissioning nuclei stays about constant in time. That is the difference between a reactor and a weapon. I see people are nodding along, so you guys are following. I haven't put you to sleep yet. That's great. And the D clearly is wrong. In both cases, you release a lot of energy. Okay, that's great. Okay, so there is a great deal we can learn about nuclear reactors if we compare it to other energy sources. So here, I'm going to compare it to coal and natural gas. All right? So let's start with coal. We go back to basics, chemical reactions. You guys have seen this over and over again in your earlier classes. So when you talk about coal, you're really talking about the combustion of carbon. Coal is carbon. Right? So the reaction is shown there is carbon plus oxygen. Where do I get the oxygen? From the air, right? From the air. I get CO2. That's the unfortunate part. That's why people no longer like coal. We've been using it for 200 years. But now we no longer like it because it generates CO2, which is a greenhouse gas. That's the bad part. And then I get some amount of energy. It's of the order of some electron volts. For those of you who remember, again, these units, okay? That's a tiny amount of energy that comes out of a chemical reaction. Okay? How about natural gas? What we call natural gas is, by and large, is CH4, which is also called methane. CH4, okay? So what does that reaction look like? CH4 plus, again, some oxygen. I get, unfortunately, CO2, bad news. I get a little bit of water. That's no problem. Goes into the atmosphere. There is plenty of water in the atmosphere. And I get 2 units of energy. Okay? So natural gas on a per reaction basis actually gives you a little bit more energy than coal. That's all good. Now let's look at nuclear. What about nuclear? So I just described it. Uranium-235 plus a neutron. In this case, it gives you a couple of nuclides there, rubidium-93, cesium-141. Those are the fission fragments. Those are the 2 lighter nuclei that come out, plus 2 neutrons. We already discussed this. Important to keep the chain reaction going. But the number I want you to focus on is the last number in that reaction. 50 million units of energy. Okay? So if from coal you get 1, from natural gas you get 2, from fission you get 50 million times. Okay? So on a per reaction basis, nuclear reactions, and fission in particular, is not 1, not 2, not 10, not 100, not 1,000, not 100,000, is tens of millions of times more energetic. All right? So what are the implications of this? And by the way, you don't see any CO2 there, which is one of the reasons why nuclear is now very interesting, is because it gives you a lot of energy but doesn't give you the carbon dioxide. Okay? So what are the implications of these basic energetics on power plants? All right? So let's take a power plant that generates 1,000 megawatts of electricity. Is that a lot of energy, a lot of electricity? It's an enormous amount of electricity, okay? So the electricity consumption, of course, is country dependent. So in the US, we tend to use a lot of electricity. We waste and waste and waste. So, 1,000 megawatt actually is enough in the United States to power a city of 750,000 people. So that would be a big power plant, okay? All right, well, let's see how much fuel I need to generate 1,000 megawatt with these 3 different technologies: coal, natural gas, and nuclear. So for coal, you would need about 7,000 tons of coal per day. Now, you guys have a big coal power plant here, maybe multiples, right? Catilina Point, right? Punta Catilina, right? Or others. What does it look like? What does a coal plant look like? Well, yeah, it's kind of dirty, yes. But there is one feature that everybody notices about a coal plant. Isn't there a mountain of coal sitting outside? There is literally a mountain of coal sitting outside. And then there is usually a railroad. Why is there a railroad? Well, because you got to feed this beast 7,000 tons of coal per day, which means you got trains coming in on a daily basis, bringing coal all the time. No coal, no power. Right? How about natural gas? Well, it's a gas, so you don't bring it by train. You have a pipeline. This plant would require 64 cubic meters of gas per second. That's, again, an exceptionally large amount of gas. And as soon as that supply of gas is interrupted, you don't get any power. Okay? So the nature of fossil plants is that unless you continuously fuel them, they don't work. How about nuclear? Well, because the energy content of uranium is so high, that power plant would require 3 kilograms of uranium-235 per day. 3 kilograms, not 7,000 tons, not millions of cubic meters per day, but 3 kilograms. That 3 kilograms is something that I can hold in my hand, okay? So that's how much energy you have in there. The implication is that nuclear reactors don't have to be refueled all the time. In fact, in commercial nuclear power plants, you put the fresh fuel, as we say, that uranium, you put it in the reactor, and then you run your reactor 24/7 for a year and a half, 2 years, sometimes 3 years, depending on what the electric utilities want to do, and without any need for refueling. Then you stop it, you open it up, extract the spent fuel, as we call it, the exhausted fuel, put in fresh fuel, and off you go for another year and a half, 2 years, 3 years, etc. Okay? So it's pretty stable, does not require a lot of fuel. Now, what else do we know, do we use nuclear energy for? You know it's used for power plants. Can you think of other applications that are kind of cool? At least one. Well, sure. I'm thinking still generating energy related, but not nuclear power, meaning for commercial reasons. You're thinking of all good applications, and that's great. The one I have in mind is we actually use nuclear reactors for propulsion of submarines and aircraft carriers. Okay, the United States uses all our aircraft carriers and submarines are nuclear powered. Russia does the same, China, it's France, Great Britain, etc. So a nuclear reactor actually powers forward, pushes forward, propels forward submarines and aircraft carriers. Now, the latest design of a nuclear power submarine in the United States is called the Virginia class. It's an attack submarine. And it's never refueled. In other words, they put the fresh fuel, the uranium, into the core, into the reactor at the beginning. And for 25, 30 years, for the lifetime of the boat, there is no need to refuel that sucker. It's amazing. And that's because the energy content of uranium is so high that you can keep going for ages without having to refuel. Okay, so big difference there between fossil and nuclear. All right, so where do we get this magical material? It's all about uranium. Uranium is the fuel, okay? So I'm going to talk a little bit about the uranium fuel cycle. Where do we get it? How do we process it? In what form does it go in the reactor, etc. All right, first thing is, like every other energy source that uses a fuel, you should ask yourself, how much fuel is out there? Right? You might have heard that, for example, in the past, people were concerned about, we're going to run out of oil. We're not going to run out of oil, by the way. There is so much oil out there, it's crazy. Same thing for natural gas. But the question is, are we going to run out of uranium? All right? So that little rectangle represents 100 years worth of uranium consumption at current rate. So if we continue to use uranium in nuclear power plants around the world at the current rate, we have about 100 years. Right? So if you focus only on uranium resources that are very cheap, then we have about 100 years worth of uranium. But we know that uranium also shows up in other resources. For example, tails of mining or tailings of mining, phosphate and shale, there is quite a bit more. So that would be 23.8 versus 7.6. That's about 3 times as much. So that's 300 years. And then if you go to additional estimate, maybe doubles. And then additional estimate, it goes up by another factor of whatever it is, 4950 divided by 8. So based on these estimates for either what we know is cheap uranium as well as tailings from other minerals that contain uranium, you could probably go on for maybe 600, 700 years, okay? You say, well, is that enough? Okay, I think it's enough. But the truth is that there is uranium in seawater, naturally. There is parts per billions of uranium in seawater. Well, there is a lot of seawater, okay? So if you look at the number there, then it becomes practically infinite. So if we're able to extract uranium from seawater, which is actually relatively straightforward, then you're looking at uranium reserves or resources that are out in the tens of thousands of years. So we're not going to run out of uranium. That's good news. Where does it come from? This is a little bit sort of US-centric, if you will. But it turns out that the best reserves of mined uranium are in Australia, United States, Canada. Now you see different colors there. Those colors indicate the price at which that uranium can be extracted. So Australia has a lot of uranium, but it's not necessarily the cheapest. So at the moment, the countries that are producing the most uranium are actually Canada, Kazakhstan, because they have the cheapest reserves. and Australia a little bit as well. So that's where we get the fuel. Now remember what I said at the beginning. What we use as fuel is the isotope 235 of uranium. That's less than 1%, okay? So the fuel, to be useful in a reactor, has to be enriched. Enriched means that you have to increase the fraction, the concentration of uranium-235 from 0.7%, which is natural uranium, up to, say, 5%. Okay, so you have these sort of different categories of enriched uranium. Natural uranium 0.7, then you have low enriched uranium between 3 and 5%. That's what we use in current reactors, so you have to juice it up a little bit. There are some advanced reactors which use 5 to 20%, and then if you go all the way up above 90%, that's what the Navy uses. And by the way, that also becomes weapons-grade material. So that's, when you go above 90%, in principle, you could use that also for nuclear weapons. All right? So there are all sorts of, as you can imagine, restrictions of how much you can enrich uranium, because then it becomes sort of more military-based material. So, but in the commercial world, we stay within 20%, which is considered proliferation resistant. Okay. Now, how do you enrich it? This is sort of an interesting process. How do I take uranium, which is natural at only 0.7% U-235, how do I juice it up to see 3 or 5%? Can I do it chemically? Not really, because uranium is uranium. So whether it's uranium-235 or uranium-238, from a chemical point of view, it's uranium. So it doesn't have, you can't distinguish between the two isotopes from a chemical point of view. So I gotta do it with physical methods. And the best method that we have now is centrifuges, okay? So first, you turn uranium, which is naturally a heavy metal, and so it's solid. You have to turn it into a gas. So you see it says there UF6, that's uranium hexafluoride. UF6 is gaseous. Okay, that's a good starting point. And then you inject that gas inside a centrifuge, which is spinning at very, very high speed. Now, why does that separate uranium-235 from uranium-238? Because the mass is different, right? The two isotopes are chemically the same, but their mass is slightly different. So when you're spinning that gas, uranium-238 tends to naturally accumulate on the outside, and uranium-235 tends to stay closer to the center of the centrifuge. Okay? So then you scoop it out, and that's how you get a little bit more enriched uranium in the middle and a little less enriched uranium on the outside. Okay, so what does this cycle of uranium look like? This is a mineral that has some natural uranium ore in it. It is traded commercially as what we call yellow cake. This is sort of a funny name for this particular chemical, U3O8. It looks like yellow powdery flour, so it's called yellow cake. All right? Then it's enriched. It's turned to UF6, and it's enriched to whatever level is needed. It's actually used in the nuclear reactor as uranium dioxide, UO2, little pellets that look black like that. It is slided into these tubes made of metal called zirconium. That's a metal that we use. This is a fuel pin or fuel rod. So this is the basic element of the reactor. And if you put together many such rods, you get a fuel assembly. This object here is maybe 20 centimeter by 20 centimeter and 4 meters tall. And then it is this fuel assemblies that go in the reactor itself. Okay, and I'll show you what the reactor core, what the reactor itself looks like in a minute. But this is the fuel assembly or fuel element that goes in. Inside each of those little tubes, you have those pellets of uranium dioxide. That's where the fission reaction takes place. Okay, that's where the magic takes place, so to speak. Okay, so let's talk about the reactor. What are the basic elements of a nuclear reactor? What do you need? Well, you need the fuel. You need the uranium. No uranium, no party, so to speak. You need a coolant. That's a fluid that picks up all that energy. If you just let that energy linger within the fuel and it keeps accumulating, what's going to happen? It overheats and melts. Okay, you don't want that. So you need to pick up that energy from the fuel rods and take it elsewhere to do something useful with it. That process is done by a fluid, typically water in our reactors, okay, that basically flows along those fuel rods and picks up the heat, if you will, and takes it everywhere, okay? So that's coolant. Then we need a so-called moderator. Moderator is fancy words for saying a material that slows down the neutrons. So the neutrons that are born out of fission have a high energy, about 2 mega electron volt. That's high, it means they go around fast. It turns out that the probability for a neutron to cause fission, which is what we want to basically sustain this chain reaction, is higher if you slow them down. If you reduce their energy from 2 MeV, mega electron volt, down to a fraction of an electron volt, tiny, tiny. So we need a material that by collision with the neutrons slows them down. That's called the moderator. And it turns out that water, which we use as a coolant, is also a good moderator. So the water that goes to the reactor does both, picks up the energy and slows down the neutrons, which is good news. Then you need a way to control that reaction. As I explained at the beginning, you know, just left alone, basically, the chain reaction would diverge. But we need to control it. We need to make sure that I can basically decide what is the power level of the reactor. How much energy do I get from the reactor? So there are some control elements. If you understood the basics of this fission chain reaction, how would you control the chain reaction? What's an easy way to control it? Any guesses? It's all about the neutrons. More neutrons I have, more fissions I have. Fewer neutrons, fewer fissions. So I can slide in and out of the core some materials that absorb neutrons, okay? And we call these the control rods. So if I have a material that is hungry for neutrons and I slide it into the reactor core, it's going to take out some neutrons and the number of fissions will come down, so the power will come down. If I extract these rods, these control rods, I allow for those neutrons to just multiply and increase, and then I have more power out of it, okay? And so that's how you do the control. And then you got a bunch of other things. The only other element that I'll mention here, you need a so-called power conversion cycle. What is that? In what form does the energy come out of fission? I said it a few times. Heat. It's heat. Calor. Right? So is that what I'm going to use at the end? Is that what the customer wants, what I'm going to sell? Not really. If I'm in the business of selling electricity, I need to turn that heat into electricity. So I need a cycle, a thermodynamic cycle that turns heat into electricity. Okay, that's what we call the power conversion cycle. I see that I'm losing the students. Is it because it's too technical or they have to go to lectures or what's the deal? Lectures, okay. Okay. All right, so this is what finally a nuclear reactor might look like, okay? A nuclear power plant might look like. We call this the pressurized water reactor. How does it work? Well, I have the reactor itself is here. Inside a vessel is a container made out of steel. Inside that vessel, I have those fuel assemblies with the fuel rods. All that uranium is in there. That's where fission reaction is taking place. Then I have a loop here with circulating water. That water is kept at very high pressure so that it doesn't boil. Okay, basic thermodynamics. If I pressurize water, I can heat it up and it doesn't boil. So that is the coolant that circulates within what we call the primary loop, picks up the energy, becomes pretty hot, and then there is a heat exchanger, which we call a steam generator, where that energy is transferred from this hot primary coolant to a secondary coolant. It's still water, but it's a lower pressure, and it's allowed to boil. So you see the energy goes from here to this blue fluid, which is water at lower pressure. That fluid boils. Now I have steam. With that steam, I drive a turbine, which drives an electrical generator, which gives you the electricity that goes to the grid. And then, as I mentioned at the beginning, I need to condense the steam that comes out here and pump it back to the steam generator. How do I condense steam? I need to cool it. What do I use to cool steam? Again, I use water. Water coming in from here, going out there. What water is that? Where is that water coming from? A river, the ocean, a lake. Okay, so that's why these power plants are usually located close to the sea or close to a river, close to a lake, because you basically need to bring in that cooling water to condense the steam. Okay? Submarine, same idea. All right, so the nuclear reactor core. So if I now take a cross-sectional view of the core itself, you see those little squares. Each of those squares is a fuel element. Remember I showed you a few slides ago? And so you got a few hundreds of those. This is what we call the reactor core. That's basically where that fission chain reaction takes place. And it has to be of a minimum size because otherwise that chain reaction is not self-sustaining. It just decays off. So it has to be of a minimum size. You can see there also the size of the vessel. Inside that vessel you have the core itself, the fuel assemblies. All right? I don't know if you can see the scale. You can see a bunch of human beings back there. For a large reactor, this is a large reactor. This generates roughly 3,000 megawatt of heat, about 1,000 megawatt of electricity, the power plant. This is the size of the reactor itself. So it's a big, big thing. Okay? Allow me to skip here, but I'll notice this is a sort of more detailed view of what's inside the reactor vessel. You can see there is a lot there. The core is down here. These are your fuel assemblies. There is another feature that I like. Thank you. There is another feature that I like to point out up here. You see this bunch of rods sticking out of the vessel. Those are the control rods, okay? So remember, as I said a few minutes ago, I can slide in and out rods of materials that absorb neutrons and control the power level. Those are the rods that I was talking about. And then, of course, you have a bunch of nozzles here to bring in and out the coolant. The water has got to be able to come in, heat up, and go out. Yes?
I am wondering how the reactor is safe.
We'll talk about safety. Hang in there. It is quite safe. It's intrinsically stable. So and what I mean by that is if there are any perturbations to the steady operation, the reactor responds to put itself back into the steady conditions. So it's designed to be intrinsically stable. But we'll get to it. I'm going to skip this. So an important element of the power plant is that turbine, that big spinning turbine attached to the generator, okay? Again, for a large nuclear power plant, 1,000 megawatt of electricity, this is what a turbine would look like. Of course, here it's been maintained, so you actually get to see inside a turbine. A turbine is a shaft with a bunch of blades, okay? It looks like a wheel, doesn't it? Right? And basically, you blow the steam through these blades and creates a torque which turns the shaft, all right? And you have multiple stages, as you can see here. So the steam comes in here in the middle, and then it blows outward this way and that way. In this case, you got 6 repeated turbines, both high pressure and low pressure, and down here is the generator. I don't know if you can establish a scale here, but you can see maybe a bunch of letters here. How long is this turbine? It's almost as long as a football field. 100 meters. Oh, yeah, 80 meters, something like that. So, and it goes around and around and around. And that's how big a turbine's got to be to generate 1,000 megawatt of electricity. It's a lot of energy going out into the grid, okay? Now, do you know how fast this spins around? How many rounds per minute? You say, wow, what is he asking me? What kind of crazy question is this, right? Why would I know? You know.
10,000.
You want to say 10,000. I want you to be absolutely precise. Because you know this. You have to think about it. What am I generating? Electricity. Okay. It's the same electricity that we get out of the wall there. Yes, I heard the magic number. 60 hertz. All right? Think about the law of electromagnetic induction, those magnets, right, that generate that electricity. You got to spin this thing at 60 hertz. Okay? So that means 3,600 RPM. Right? That's how electricity is made. All right. Now, let's think about this old power plant as a big black box. Big black box. What goes in is heat from fission. What comes out is electricity. That's all good. Wouldn't it be lovely if I was able to turn all the heat that I get from fission into electricity? That'd be great. That would be a 100% efficient power plant. But guess what? Whether it's a nuclear plant or a coal plant or a wind or solar, the laws of thermodynamics always apply. There is no shortcut. There is no exception ever, ever, ever. Okay? So in particular, there is a second law, this pesky second law, which always, always limits the efficiency of systems. All right? So according to the second law of thermodynamics, a power plant that takes in heat either from fission or gas or coal or sunlight or geothermal, whatever, and gives you electricity, also has to discharge some waste heat, cannot convert 100%. There is some heat that has to be discharged to the environment. So I can define then an efficiency for the whole power plant, which is defined as the net electric output, which is what I want and what I sell to the grid, divided by the amount of heat input that goes in, okay? And so representative values for this thermal efficiency are shown here. This efficiency really depends on the temperature at which the steam is generated, the steam that drives the turbine. The hotter the steam, the higher the efficiency, all right? So coal plants and natural gas plants, CCGT means combined cycle gas turbine. So that's a natural gas fire plant. And coal plants tend to operate very hot, very high temperature. So they have a good efficiency of conversion of heat to electricity, let's say between 38 and 60%. 60% is really spectacular, okay? And by the way, I understand that you have now in the Dominican Republic the latest CCGT, combined cycle gas turbine that is very, very efficient, so that's good news. Nuclear reactors tend to operate a little bit cooler, not as hot, and so their efficiency of conversion of heat to electricity is a little bit worse. Now, there is a whole new set of nuclear reactor designs, they're called advanced reactors, which operate at a higher temperature, generate that heat and steam at a higher temperature, and therefore are expected to be more efficient, okay? But one way or another, you cannot convert all heat to electricity. You gotta pay your dues to the second law of thermodynamics, okay? Now, the implication of this heat discharge to the environment is, as I said earlier, that all these power plants ought to be located close to what we call a heat sink. It could be water from the ocean. It could be water from a river here going into a cooling tower, or if it's a submarine, well, it's again water from the ocean. Okay, but some of that energy's got to be sort of released back into the atmosphere. All right, so here comes the second little homework here, or quiz. So if the thermal efficiency of a nuclear power plant is 33%, and that plant generates 1,000 megawatt of electricity, what is the thermal power? What's the heat that comes out of the reactor? I got to get to 1,000. I have an efficiency of 33%. What do I need to start with, fission-wise? 3,000. 3,000, okay? So there you go. How much heat is rejected to the environment in this case? So I start with 3,000 megawatt fission. I give 1,000 of electricity to the grid. I see here people are doing 2,000 got to go to the ocean or whatever it is, okay? So this efficiency is a big deal, unfortunately. If it was close to 100%, it would be great, but we got to sort of waste all that energy. Second law of thermodynamics. What are the downsides associated with heat rejection in nuclear power plants, or for what is worth, in any other power plant? Reduction in electric output for a given thermal power rating of the core? Yes, absolutely, that's the efficiency business. Thermal pollution, I haven't talked about this. Can you just discharge this heat into the ocean? No problem. Why not? You're raising water temperature, fish may not like it, so there are very strict regulations, okay? You cannot just dump water at 90 degrees C into the ocean because you're gonna boil fish, okay? So you don't want that. So there are strict limits on how hot you can return your water to the ocean or a river or anything like that. Additional costs associated with heat rejection equipment. For example, I need a condenser, or all of the above. All of the above. All of the above. Do you like the little quizzes or not? You good? Okay, so we talked about where do we get uranium, what do we do with it once it's in the reactor. I showed the reactor. Now, what happens at the back end of the fuel cycle? Once I take the fuel out of the spent fuel or exhaust fuel out of the reactor, what happens then? That's what we call the back end of the uranium fuel cycle. Okay. So the first thing I want to impress in your mind is what people call nuclear waste is the fuel, the spent fuel that comes out of reactors. Unlike a coal plant or a natural gas plant, there is nothing burning here. You don't start with a material and you burn it and you let it sort of spew into the atmosphere. That's not a nuclear reactor, okay? The fuel, the spent fuel or waste, is still the fuel assembly. Does that look any different than when it went in? Not at all. Still the same thing. Now, who here likes the Simpson, the Simpson cartoons and all of that? At least you must have seen it. You like it or you've seen it. Okay, so Homer Simpson works at a nuclear power plant, is the worst possible example of a nuclear operator. But on occasion in that cartoon, they show you nuclear waste. What does it look like? It looks green, glowing, fluid ooze coming out of barrels. Okay? No, it doesn't. This is the nuclear waste. It looks exactly like it went in. What's the difference? The difference is that some of that uranium-235, which was our fuel, has now become those fission fragments, those fission products. Those products are radioactive. So it looks the same, but it's highly radioactive. That's why it's waste and it has to be handled carefully. But it's not green, it doesn't glow, and it's not liquid ooze coming out of a barrel, okay?
You're saying that the Simpsons are not educating us?
Yeah, they're not, unfortunately not.
How come?
I don't know. The Simpsons are scientifically very incorrect. It actually is even more interesting than what I just said, because not only it looks the same, but most of the material I have in here, 94 to 96%, it's still uranium. Now, remember what I said at the beginning. Uranium that we put in the reactor is how enriched? What do we say? What's the enrichment level for uranium that goes in? Let's say 5%, okay? And what we use is only that 5%. The rest is uranium-238, which is there, is not doing anything. So that uranium-238 still comes out and constitutes 94, 96% by mass of what went in. So that's still material that I could separate, and it's still uranium, and that's good. About 3 to 5% is the fission products. FP here stands for fission. This is the real garbage, okay? That's the radioactive stuff that I want to get rid of. Only 5% of this mass or this fuel element is the garbage. And then there is a magical new element here in the middle. Pu, that stands for plutonium. Plutonium. Now, if you look at the periodic table of the elements, and if you had looked at the periodic table of the elements up until 1938, 1940, whatever it is, it would have stopped where? What was the heaviest element in nature? Uranium.
Non-reactive, no?
Well, uranium is, I mean, unless you put it in a reactor, is just perfectly stable, yeah. So it would have stopped at uranium. Those are naturally occurring elements. Well, plutonium as an atomic number that is number two higher than uranium. So uranium is Z equal 92, plutonium is Z equal 94. It's not a natural element. Where does it come from? It's artificially produced within the nuclear reactor itself. How? Well, remember I told you this uranium-238, the isotope that we think it's useless. It's kind of useless, but not entirely useless. every once in a while, it captures a neutron, and then after a couple of radioactive decays, it becomes plutonium-239. So as you use your fuel in the reactor, you actually produce also a little bit of plutonium. Now, why is plutonium important? Because plutonium-239, just like uranium-235, can do fission. So it's actually good fuel, all right? So in the spent fuel that you get out of a reactor, this is the garbage. This is very valuable if you decide to reprocess the fuel and separate it. And this is also potentially recyclable, okay? It's a little bit of uranium with some uranium-235 in it and so on, all right? So 96% of a spent fuel assembly is still valuable. That's the point. Well, with that in mind, what does the back end of the fuel cycle look like? Let's say, well, we already talked about I mine it, I need to enrich it, I fabricate the fuel, I put it in a reactor, and then if I do what we do now in the United States, once the fuel comes out of the reactor, it's put in an interim storage. It's just sitting there to cool down, basically, okay? So you naturally let that radioactivity to go away. And then finally, you do direct disposal. So you put it into a form that is a little bit more stable, and eventually you put it underground. This is called the once-through fuel cycle, okay? So there is no recycling, no reprocessing. It goes through. But it's not the only option. If you understand what I told you 2 minutes ago, there is still a lot of valuable material into that spent fuel that comes out of the reactor. So other countries, for example, France, Japan, Russia, and even China, reprocess the spent fuel. So the front end is the same. I put it in a reactor. I still put it in interim storage for a while. You want the radioactivity to decay off a little bit, because otherwise it's very difficult to handle. But in France, they actually reprocess the fuel. What it means is that they separate the garbage, the fission products, that's the waste, from what is valuable, plutonium and uranium, and it's put back into a fuel fabrication, and then it goes back into the reactor. And you can do that cycle a couple of times before the uranium becomes basically no longer useful, and then you got to trash it. But you get a little bit more energy, a little bit more value out of your overall chain if you do that reprocessing. What's the downside of this? Why aren't we doing it in the US? It's not that we're smarter. The French love this. They do it, they'll do it. But if you were to see, pros and cons of this, what would you say? It's more costly and complex. This, here on a slide, everything looks simple. It's not simple. This plant are very, very big, costly plants, okay? Billions of dollars to build, and they add cost and complexity. There is another pesky little issue with this approach. I separate plutonium, okay? Plutonium is great fuel for reactors, but unfortunately it is also great fuel for nuclear weapons, okay? So when you do this little recycling, you introduce, theoretically, the possibility of separating plutonium and then using it for weapons, okay? So if you decide to go this way, the International Atomic Energy Agency, the United Nations essentially, will make sure that these facilities, these two plants, the spent fuel reprocessing and fuel fabrication, are continuously monitored so that that plutonium is not diverted to weapons use, that is used just for civilian purposes. Right? So lots of complexity. Okay, so what are the takeaway messages? What did we learn? First, I hope I impress in your mind that this nuclear energy is a very high energy density, very high density source. There is nothing close to that in the universe. You can't beat nuclear, okay? It's just so intense. It's also emission-free, which is why now is back into the debate in a big time. It doesn't have any CO2 going into the atmosphere. Uranium is plentiful. It says especially in Australia because I gave this presentation in Australia, so I wanted to let them know that they know it. Nuclear reactors produce heat, which can then be converted to mechanical work and electricity. And then, as we just discussed, both open and closed fuel cycles can be realized, okay? So hopefully that gives you sort of an introduction to nuclear energy. Let me stop here. Let's take a few questions. And then if you are interested, I can just spend maybe 10 minutes or so telling you what's going on now in nuclear technologies. What's, advanced reactors. Could this technology make sense for the DR or not? Okay, but let's see if you have any questions or comments on what we've just presented here. Don't be shy. Yes, sir. One, but also no, I think the gentleman in the back there.
He's saying he's going to allow me to talk.
Okay, sure. Caballero.
Hi. Okay, so my name is Raquel Matos. I am doing my bachelor degree in chemical and paper engineering in Michigan, and I am considering to do my PhD in nuclear energy science.
Mm-hmm.
So I just would like you to give me any advice in that journey, because my family thinks it's dangerous. So I'm just curious.
It's a great discipline. If what I presented here sort of intrigues you, then go for it. University of Michigan has a great nuclear engineering program. Of course, the one at MIT is much better. So you should apply to MIT. You are applying to MIT? Yeah. Okay. I'm going to talk a little bit more about safety if we go into that second part of the presentation. But the safety record of the industry is actually very, very strong. Now, you're familiar with the accidents. Everybody knows about Chernobyl, Fukushima. But in a way, it's ancient history. The technology evolves. It's a little bit like saying, I don't want to fly because a plane crashed 30 or 40 years ago. So, every accident has resulted in improvements in the technology, retrofitting of the existing nuclear plants, et cetera, so that class of accidents could be greatly minimized or eliminated altogether. So if the Dominican Republic were to go into nuclear energy now, you would build older plants that are safer than what was in the plant. That's always been the evolution. But honestly, the existing set or park of reactors out there is already exceptionally safe. Okay, here, but I want to make sure also the gentleman in the back, because he's the first one that raised his hand, gets to put his question in. So let's go to him, and then our beloved student here. Please go ahead.
Okay. Hi, my name is Armando. I'm Tavares, and I'm also a teacher here in Intech. And I was curious about what's the neutron source?
The question I think you have is, how do I get these things started?
Yes.
Right? So it's clear that once you have fission, then you have a lot of neutrons out there. So there are neutron sources. This is actually very straightforward. We use antimonium, beryllium. Antimonium spits out alpha particles, and the particles impinge on beryllium, which knock out a bunch of neutrons. Okay. So a neutron source looks like a can of soda, like a can of Coca-Cola. Inside you have this material that basically spits out a bunch of neutrons. Once these neutrons are out and you get the chain reaction going, then there is no need for a neutron source anymore.
Thank you. I had another question, but it was related to SMRs and thorium, but
yeah.
Probably you're going to get to that.
I will, yeah.
Okay.
I'll talk about the SMRs in a minute.
Problem.
Yeah. Sir. You, yes, I think.
Bueno, voy a hablar en español para que se lo traduzcan.
Go for it, but then someone's got to translate for me. Yeah.
Una de las cuestiones que la gente más le preocupa de la energía nuclear es lo supuestamente extremadamente peligroso.
Mm-hmm.
Eso ha dado, por lo que yo he leído, porque yo no soy de la energía nuclear, soy nuclear pero no de energía. Entonces, está muy de moda poner al público del conocimiento de que las plantas nucleares que están de moda, que son las de pequeñas plantas nucleares, tienen una alta seguridad, a diferencia de las viejas plantas nucleares de miles de megavatios. ¿Podría explicar en qué consiste el hecho de que esas plantas pequeñas, como la que usa Argentina, o está fabricando en Argentina, por qué, y creo que también en Sudáfrica he leído en algunos artículos, por qué son más seguras que las actuales plantas.
Yeah.
¿En qué consiste esa seguridad?
I don't need the translation. I got it. Yeah. The question is, why are smaller reactors safer than larger reactors? It turns out that Italian and Spanish are actually pretty similar, so I can understand. My answer is actually they're not necessarily. So I think this is a little bit of propaganda, honestly, a little bit of marketing that they say the smaller reactors are safer. All the reactors that are being developed now, whether they are 1,000 megawatts or 100 megawatts, use what we call passive safety. That's been the big improvement, or intrinsic safety. So in traditional plants, in order to maintain cooling of the reactor, which is sort of the mantra, it's one of the requirements of nuclear safety, there are engineered systems that rely on pumps. And what we know about pumps, in order to drive a pump, you need some electricity. You need some diesel generator, some energy source. So no external energy source, no pumps, no safety. That's the traditional approach. So in traditional plants, the goal of a major goal of safety is to ensure that you have such redundancy of pumps and diesel generators and energy sources so that the probability of having a blackout, if you will, and not being able to use your safety systems is very, very low. That's tradition. That's the past. All the new reactors have shifted to a system in which you don't need pumps and you don't need diesel generators. And so you use things like thermosiphoning, natural circulation, buoyancy, pressure gradients, gravity. It's not as efficient as the old system, but it's much more reliable, because even if you run out of diesel generators or the pumps don't work, you're still going to maintain the cooling of the reactor. So it's not really the size or the power output, small versus large, is more, are they active, do they use active safety or they use passive safety? That's the big divide. And all the new designs use passive safety. Very good question. In a way, I'll get back to it in a minute. You wanted to ask a question, or either one, or both.
Well, hello, Professor. It's an honor to be here. I'm a mechanical student, first period, and my question is related to nuclear fusion. Well, with recent progress in nuclear fusion, what are the biggest technical obstacles left before we can have fusion power plants, and how soon do you think we could overcome them?
Okay. So the question is about fusion. I've talked about fission, okay? So fission, as you saw, is the splitting of a nucleus of uranium, heavy nucleus, into two halves. Fusion, in a way, is the other way around. You start with two very light nuclei. It could be H2 and H3. Those are called deuterium and tritium. So they're two isotopes of hydrogen, very light. You put them together, and you get helium, plus a neutron, plus a lot of energy. Okay, turns out through the magic of quantum mechanics and nuclear physics that it works well. In other words, you get energy out of that process, just like you get energy out of the fission process. Now, what's the challenge in making fusion happen? Well, the challenge is that while a neutron is, by definition, a non-charged particle, it penetrates a nucleus of uranium-235 effortlessly, very easily, and once it's in, it splits it. But in order to pull together two nuclei, like deuterium and tritium, that are charged, because the nucleus are positively charged, what do I need to do? I need to overcome what? The electric repulsion, okay? Because they are both positive, so they want to move away, but I want them to come close enough such that the strong force, the strong nuclear force, finally pulls them together and fuses them, okay? How do I pull them so close that finally the two nuclei will fuse? Well, either I have an accelerator and I literally smash them into each other, in which case it's okay, fusion occurs. But that is not a power plant, okay? Or I have to heat them up so much that just because of their thermal agitation, their kinetic energy is so high that every once in a while, when they bump into each other, they've gotten close enough that finally they're fused together. So when I say heat them up, I really mean it, guys. So not 1,000 degrees, not 10,000 degrees, 10 million degrees, okay? So now, how do you heat up something to 10 million degrees? And most importantly, how do you keep it contained? Because anything that comes in contact with 10 million degrees is going to melt instantaneously. So you can create some form of a magnetic bottle. You generate magnetic fields that are so strong that basically bottle up these called plasma, okay, this plasma, and allows it to survive or to exist at a humongous temperature without touching anything surrounding it. All right? So this happens in a tokamak, which is the Russian word for toroid or torus. And so in this tokamak, in principle, you can do fusion. Now, finally, I'm getting to your questions. How close are we? I'm not a fusion person, so I can't tell you too much about it. But I work with colleagues at MIT that are 100% focused on fusion. And what they told me is that the big technological breakthrough that has happened in the past 10 years has been the development of superconducting magnets that create monstrously strong magnetic fields, such that this magnetic bottle confinement of plasma can be done very efficiently. So efficiently that the size of a tokamak, this big machine, goes from being as big as 3 times this room to down a fraction of the room. And so the excitement there is that now they think they can prove this fusion approach on a much smaller scale, cheaper and faster. So then finally, you ask, when do we have fusion plants? In your lifetime, maybe in my lifetime, but don't hold your breath. This is not imminent, okay? Because at the moment, they still have major engineering challenges to face, related to materials, related to the performance of these magnets that I just mentioned, related to the breeding of tritium. I haven't even gotten into this, but to get a fusion reaction going for the longer term, tritium is not a natural occurring material. It's got to be bred. It's got to be produced within this plant. And it's not clear that they have a tritium balance that will allow this tokamak to sort of grow in numbers over the years. So a lot of challenges. I gave you a very long answer to a simple question.
Yeah,
but there is a lot going on. It's exciting. It's not going to be within 10 years that you'll call your electric utility and say, I want semi-electricity from fusion. So, yeah.
Okay, it seems we have the technical aspect kind of figured out already. But how do we get the average person to trust it? Like, this talk is being given to engineers who probably already trust this technology. But what about the average person? When in media, the plants keep getting represented as wasteful or dangerous.
Yeah, that's a great question. So, how do you get the so-called, what we call a social license? So, first I would say people that live near nuclear power plants tend to be the ones that support them the most. Okay, so in the United States, on average, if you look at surveys at the moment, 68, 69, 70% or so of the general public say, in general, I'm in favor of nuclear, I actually want more reactors. But there are some massive spikes in support when you go to counties and towns that actually host nuclear power plants. And that's because these people have been living next to nuclear power plants for decades. They maybe know a neighbor that works at the plant. So there is a level of comfort with the technology. Now, I'm not a communication expert, but what I've learned over the years is that the messenger matters as much, if not more, than the message. So the last thing, if the nuclear industry wants to be successful, that they should do is to send people like me or nuclear engineers up in front of the cameras and tell people how safe, how great this technology is. That doesn't work because there is a credibility gap. You say, okay, yes, I understand you understand the technology, but it's your life, it's your work, maybe you have a vested interest, so why should I trust you? Much better if you send people that are not related to the industry, but they understand the value of the technology and its societal benefits. And so at the moment in the United States, there is a whole new generation of young people like you that think that nuclear could be useful for mitigating climate change, reducing emissions in the electric system or in other sectors of the economy. That they think that it's a good energy source because we have plentiful fuel, because it doesn't use a lot of land, which is another aspect that I'll mention in a minute, as opposed to wind and solar that use a lot of land, et cetera. And so if people with no vested interest get to advocate for the technology, I think is much, much more effective. Well, another thing I learned is that People trust you if you establish shared values. They don't trust you out of authority. I can say I have, a PhD in nuclear engineering from MIT, therefore you should trust what I say. I can say here because we are in academia, so you guys should trust me. I'm not telling you BS. But in a public forum, first you need the audience to feel that you share their values. So our kids are going to the same schools, or we live in the same county, or we want the same thing for our country, etc. Once there is that shared ground, then you can talk about challenging questions like nuclear waste or nuclear safety with some effectiveness. So share value first, good messengers, then people trust you. Any other questions or comments? There is one there, yeah. Or maybe not. Okay, so if you're not exhausted, we can go into the other talk. This is still me. Okay, so this is my second time in the Dominican Republic. I love it. Great island, and you guys are warm. Last night we had a wonderful dinner. The food is great. That's it. I understand the economy is okay, dynamic. I mean, clearly there is a vibe. This country is on the rise and all of that. All that is positive. The energy picture is pretty ugly, okay? It's ugly. You don't have domestic energy resources, so at the moment you import 90% of your energy from outside in the form of gas, coal, oil, and so on. This is energy, okay? So it's everything, not just the electric power sector. It's transportation, is factories, industry, everything together. Now, if you go into the electric power system, at the moment, 85% of your electricity comes from fossil fuels. I'm sure you've heard a lot about, hey, we're building solar plants, we're building wind. They're doing that, but it's still a tiny, tiny little fraction, okay? And when you look at actual electricity generated, by and large, still comes, I think, in this country from coal, natural gas in particular. All right. This makes your electric grid very carbon intensive, all right? So what do I mean by carbon intensive? Well, a way to measure how much emissions you produce in your electric power sector is to look at the grams of CO2, mass of CO2 emitted per kilowatt hour of electricity. Okay, kilowatt hour is a unit of energy, of electric energy. So at the moment, the DR power sector emits 630 grams of CO2 per kilowatt hour. Is that high? Is that low? World average is 500. So it's a little bit higher than world average, but it's monstrously higher than other countries that have managed to decarbonize their electric power sector quite a bit. So for example, France, which by the way uses mostly nuclear power, is down to 70 grams of CO2 per kilowatt hour. Norway, which uses no nuclear power but uses all hydro, also carbon-free or low carbon, is even lower than that. It's, I think, 40 or 50 grams of CO2 per kilowatt hour. Okay, so there is a long way to go. So if you care about reducing the emissions in the DR, you got to go from 630 down to less than 100. Very, very, very long way. So with this picture, which is not particularly pretty in terms of energy, the question is, can nuclear play a role? All right, so well, let's see. So the first question that I often get is, all right, I understand that a nuclear reactor does not emit CO2, but what about the emissions associated with mining the uranium, processing the uranium, making the fuel, transporting, decommissioning the plant? Well, I got bad news for you all. There is no such thing as a zero carbon energy source. Not solar, not wind, not nuclear. All energy sources emit some CO2. Why? Because if you look at the life cycle, you know, the materials you gotta mine to build the solar panels or the nuclear plant, and you look at the emissions incurred in transporting that material from the mine to the fabrication facilities and from the fabrication facilities to the site and then decommissioning, et cetera, et cetera, et cetera. There is some CO2 emissions associated with all of this. Having said that, clearly fossil fuels, which emit as you're generating electricity, are worse. And so you have here grams of CO2 per kilowatt hour, not surprisingly, coal, natural gas being very, very high. And then at the other end of the spectrum, you have low carbon. So from this point on, I'm going to call it not zero carbon, but low carbon. And in the low carbon section, nuclear is actually one of the best, as you see down there, along with wind. Okay. By the way, solar panels, PV, that everybody likes, 4 times more carbon intensive than nuclear or wind. Okay. So again, keep in mind, no zero. All right. Another good feature of nuclear is that it's very compact. Nuclear plants don't tend to to consume a lot of land. It all stems from the high energy density of uranium, right? So all the energy comes from that little material there. And I showed you already, 3 kilograms per day, you get 1,000 megawatt of electricity. So the plants tend to be very compact. Not only that, but they're not intermittent. They're not subject to weather. Whether the sun shines or does not shine, the wind blows or doesn't blow, a nuclear plant always is on, always generates the electricity. So is, by the way, a coal plant or a natural gas plant. They're not intermittent. By contrast, of course, solar and wind, great energy sources, okay? They become very cheap and they don't emit emissions when they are in generation. But they take up a lot of land, as you guys have seen, right? You might have driven next to a solar field. And they're intermittent. They're not always on. So we use these words or this parameter that is called the capacity factor. The capacity factor, 100%, means that if a plant is designed to give you, say, 100 megawatts, and it has a capacity factor of 100%, it means you get that 100 megawatts all the time, 24/7, 365 days a year, okay? Well, what is the capacity factor for a nuclear plant? Pretty close to 100%, right? So they tend to be very, very reliable, 100%. And they don't take up a lot of land. So you can think of a figure of merit or a metric that says how much energy am I getting per square kilometer or square mile or whatever you want to use. So for nuclear is 2,200 plus megawatt of electricity per square kilometer. What about solar and wind? Well, their capacity factors is much, much lower because, again, they're weather dependent. So for solar, it's typically less than 30%. For wind, is less than 40%. And as you said, they take up a lot of land. So what is that figure of merit for those two? 6 megawatt per square kilometer, 1 megawatt per square kilometer, respectively. Okay, so there is a factor of 1,000 to several hundreds difference in the compactness or land usage of nuclear versus renewables, right? So that's something to keep in mind, I think, particularly for a country like the DR, which is not enormous. You can't carpet cover the whole country with solar panels. Now, again, this is not a either or. You probably want both, but the point is a big difference there. Okay, so what's the contribution of nuclear energy now worldwide? What I focus on here is low carbon electricity. So don't think coal, don't think natural gas, don't think oil. Just think about those energy sources that give you low carbon electricity. That is nuclear, hydro, solar, wind, geothermal, biomass, that kind of stuff. All right? So if you look at the relative share of low carbon electricity worldwide for nuclear is about 30%, 45% or so is hydro, and another 25% is solar and wind. But in the United States, we rely, relatively speaking, more on nuclear. So roughly 50%, half of our low carbon electricity at the moment comes from nuclear power plants. And then roughly the same, actually a little bit more solar and wind than hydro. Similar situation for the European Union. China is big on hydro. They got massive hydro dams. And the Republic of Korea, which is here because I gave a similar presentation there a couple of months ago, relies astronomically on nuclear. And so you see 80+% of their carbon-free electricity, or low-carbon electricity, is nuclear. So the point here is that it's all country dependent, of course. Not all countries are using nuclear, and not all countries that have nuclear are using it to the same extent. But it's already an important piece of the clean energy infrastructure of many countries and the world overall. Having said that, what are the trends? In which countries is nuclear going up? In which countries is staying constant? In which countries is going down? So if I look at the global scale, countries that are building a lot of new nuclear power plants are China, by far. Okay? Half of the nuclear power plants under construction now are under construction in China, okay, half of them. So that's a big push. India is tripling its capacity, nuclear capacity, as we speak. Russia has been building all along, domestically and internationally. The Middle East now, they have several nuclear power plants. The Emirates, Dubai, Abu Dhabi, they now get 1/4 of their electricity from a single nuclear power plant with 4 reactors, okay? And they had none in 2009, when they made the decision to start the nuclear program. So they went from 0 to 25%, 1/4 of their electricity being nuclear in 15 years. That was pretty impressive. Eastern Europe is also pushing. What about Western Europe, Japan, and the US? Stagnant or declining? Declining really in Japan because they had the accident, they've gone down big time. Western Europe and the US, there is a lot of interest. I'll tell you maybe a little bit more in a few minutes about the interest in Europe and the US for nuclear. But we're not seeing a lot of new projects being built. Certainly not at the same level of China, India, Russia, etc. So that's sort of the scale or the global picture. Let me skip this one. All right, so now we get to talk about what technologies, what reactor designs are being developed now, what's available. All right. So there are essentially 3 classes of reactors. The first is large reactors. We call them large light water reactors because the coolant is water. By the way, you might ask, why do I say light water? That's H2O, because there is another reactor type, which I'm not going to mention other than now, that uses heavy water. What is heavy water? It's still H2O, but the H is not H1, is H2, is deuterium. Okay, so anyway, in Canada, they like that better as a coolant than light water. But this, the first class is sort of traditional, gigawatt, okay, 1,000 megawatt and plus. There are some designs, 1,600 megawatt, 1,600 megawatt of electricity, really, really big. How much do they cost? Well, it really depends on who builds them. The Chinese, the Koreans, even the Russians are very good at building nuclear plants. Okay, they've been doing it continuously over decades and decades, so they've gotten pretty good. So you might be close to $2 or $3 billion for a gigawatt. That's actually pretty cheap. I know $1 billion sounds like a lot of money, but it's also a lot of electricity that you get. In Europe and in the United States, where for many years we did not build new plants, these large plants are now coming in at $10 billion, $10 billion. Now that's expensive. Right? How long does it take? Well, again, companies that are really good at building them, they build these large plants in, say, 5 years. Companies that are not as good may take twice as much. Right? So that's the first category. Second category, small modular reactors. Well, they should be called smaller modular reactors because, yes, they're smaller than that. Instead of a gigawatt, here you're down to 70 to 300 megawatt. There is that range because there are so many different designs and I wanted to catch them all, okay? But you see now you're down an order of magnitude in terms of power output, all right? How much are they going to cost? Well, still not cheap, I'm talking billions. The theory there is that it might take as short as 3 years to build. It's still a large construction site, okay? Still sort of, you have to excavate, there are concrete domes and things of that type. And then finally, there are what we call micro reactors. I also call them nuclear batteries. Now, those are really tiny. Now you're down to a few megawatts or 10 megawatts, okay? And the idea here is that they would be built in factories, not a big sprawling construction site, but factories, a little bit like trucks or, not like iPhones because the size is still bigger, but truck-size systems, okay? So more efficiently. Now, if you think about the Dominican Republic, where would it make sense? Yeah, either small modular reactors or micro reactors. Why not large? Because your grid is not that big. What is the total capacity, Manuel? You told me yesterday or someone said?
The peak is
7 or something, I thought, the peak?
3,600.
3,000, okay, so imagine, your peak demand at the moment is 3.6 gigawatts. Here, we're talking about a single plant taking half of the peak, too much, okay? Because for whatever reason, that plant is down because it's been maintained, refueled, then half of your grid is out, okay? So it doesn't make sense. But 100 megawatts, 200 megawatts, and maybe multiple of those, that would make sense. And then, of course, down microreactors. Microreactors are interesting because you wouldn't necessarily connect them to the national grid. You could serve local loads. It would be more like microgrids, if you guys know what that means, right? So instead of being connected with big transmission lines, you would generate the electricity and then use it right there where it's generated. Okay, I'm going to skip all of this. I'm definitely going to skip this. Let's talk a little bit about safety. Okay, so whether it's a gigawatt or a small modular or a micro, all these new technologies now adopt this passive safety concept that I mentioned a minute ago. Okay, so that's a combination of design features. For example, they could use a different coolant. Some of these don't use water as a coolant. They use helium, or they use molten salt or liquid sodium. These are coolants that don't boil off. So you don't basically, even if there is a leak or something, you're not losing your coolant. You are able to maintain heat removal from the reactor core. They might also have fuel forms that are no longer the uranium dioxide pellets that I showed you at the beginning, but there might be particles with multiple layers that are very robust. What that means is that even if the temperature inside these reactors rises to very, very high level, the fission products, which are the radioactivity, do not basically diffuse out. So that's all good news. And then, as I mentioned, safety systems that do not require external intervention. They do not rely on pumps or diesel generators to function. So what's the implication of this approach? Is that accidents like 3 Mile Island, Chernobyl, and Fukushima are truly eliminated by design, okay? So that class or that type of accidents cannot happen, physically cannot happen. Does that mean no accidents can happen? Obviously not. Anything that is engineered can fail, so you can still have failures, malfunctions, whatever you want. But the consequences of these failures, malfunctions, and accidents would be a lot more benign. That's the point, okay? They would be a lot less severe. In fact, in the United States now, the Nuclear Regulatory Commission, which is the government agency that regulates the nuclear industry, has allowed these new reactors to shrink what we call the emergency planning zone, the area surrounding the plant, down to site boundary, like 100 meters or even less from the reactor itself. What that means is that anybody living outside this emergency planning zone does not have to evacuate if there is an accident, does not have to take iodine pills and things of that type. So this reduces anxiety, it reduces cost, honestly, and makes the whole thing a lot easier to approve. Getting to the end here. What are you going to use nuclear energy for? Well, the first and most obvious is the grid, the power grid, okay? They could replace coal plants, they could replace natural gas plants. Actually, this is fairly straightforward. For coal plants, coal plants operate base load, which means also operate 24/7. You don't like coal because it has the emissions, replace it with a nuclear plant, roughly same size, same idea, 24/7. Natural gas plants in virtually everywhere in the world, they don't tend to operate base load, always 24/7. They are so-called spinning capacity, sometimes in reserve, so that if, for example, there is a need for a rapid increase in power, a natural gas plant can respond very quickly and give you that decrease in power. So how do you replace a natural gas plant with a nuclear reactor? Nuclear reactors are not happy when they go up and down in power very rapidly. So one approach that is now being tested in the United States by TerraPower, that's Bill Gates' nuclear company, is to run the reactor at 100% output, store the heat at the site in liquid salt tanks, and then use that heat to generate electricity in a variable manner. So if the grid requires more power, I can give it more power. If the grid requires less power, I can give it less power. And I can do that very, very rapidly because I have decoupled the production or the generation of electricity from the heat production of the reactor itself. Okay, so it's kind of a clever scheme. which should actually increase the amount of revenue that such nuclear plant will be able to bring in. Why? Why does it increase revenue? Why does it increase sales? Because when the grid demands more power, it probably means that electricity prices have gone up, okay, supply and demand. So if the prices are higher and I sell more, I make more money. If the prices are lower, the demand is low, right? And I hold the energy there, then I'm not selling cheap electricity. So it's a revenue-making approach. Okay, so that's the grid. But there is much more than the grid. Do you know what fraction of CO2 emissions is associated with power production on the grid? How much CO2 comes from electricity production on the grid? What do you think? 10%, 50%, 100%? About a quarter. About a quarter, 25% of all CO2 comes from electricity production. About the other 75%? Cars, trucks, factories, buildings. Where I live, in the winter it gets cold, so we turn on our heating. Now here, you're lucky, it's always warm, so you had the heating problem, you got the air conditioning, so you're back to electricity. The point is, other sectors of the economy emit a lot of CO2. So how do we decarbonize other sectors of the economy? For example, how do you decarbonize transportation? Because at the moment, we just use gasoline or diesel. That's fossil fuels. Yes, that's absolutely. That's a good answer. I'm a big public transportation fan. I take the subway every day. Sure, if we, instead of driving the stupid cars every day, if we took public transportation, emissions would come down. But eventually, even if we took public transportation, that public transportation got to be low carbon. Otherwise, you still have emissions. So how do we decarbonize? Any other ideas? Electric vehicles, okay. So now, good. So now I'm back to the electric grid, okay. If we were to use electric vehicles instead of gasoline vehicles, then we would need to produce a lot more electricity. And that electricity ought to be clean, otherwise you're back to emitting CO2. Any other ideas? Why do I have hydrogen there? Say it again? For CO2, you want to capture it at the tailpipe? Very expensive. Let's see what it says. Say it again. So electric vehicles require electricity to charge the batteries. That electricity could come from nuclear reactors. Yeah, so that's one approach, yeah. Back there, hydrogen enthusiasts?
Maybe hydrogen for fuel cells or
yeah.
combustion?
Or sustainable fuels that are chemically identical to fossil fuels, but they come from a different source. Yeah. So look, what I'm fishing for here is, you might have heard about hydrogen, okay? So hydrogen is not a primary energy source. You're not mining it. It's not like oil. You're not sort of drilling and finding hydrogen. It doesn't work that way. You got to make it. How do you make it? The best way to make it is to split H2O, water, right? We got water all over the place. That's called electrolysis. Electrolysis, right? You guys have done the experiment in chemistry. You stick two electrodes in a bucket of water, and you get oxygen at one end, at the cathode, and at the anode you get hydrogen. You've done that, right? So you can get your hydrogen, which then is used for fuel cells in cars or trucks, but it requires electricity in, okay? And if you actually heat up the water to begin with, that process becomes even more efficient. So all these lengthy introduction, just to say that you could use nuclear reactors to make hydrogen. And you can do that on a grand scale, like shown up there, where you have your reactors right next to a chemical plant, an electrolysis plant that splits water. And then you have this enormous amount of hydrogen, and you can send it to markets either by tanker. You got to liquefy it in tanker and put it in tankers, or you can put it in a pipeline and send it that way, okay? But the energy's got to come from somewhere. And if it comes from nuclear, is no CO2, right? So that's the idea. I'm going to skip this. Okay. So, last couple of slides, and then I'll let you go. Support for nuclear, all right? So, nuclear has this sort of reputation, nobody likes it. That's actually not true. In recent years, things have changed quite dramatically, okay? First of all, there is quite a bit of private capital investment. If you think about the history of nuclear energy, it all started back in the Manhattan Project in the United States. It was used for weapons at the beginning, okay? And then it became used for propulsion, submarines. Then it became finally the good use that we like, which is power, you know, electricity for civilian uses and all of that. Well, throughout this whole history, it was very much the domain of the US government or governments around the world. It was very top-down. You know, this is, we need it, so the government puts billions of dollars into developing and testing and all of that. That is still substantially true, but what we've seen in recent years is a substantial amount of private capital coming in to support the development of new nuclear technologies, okay? In the United States, at the tune of $4 billion, right? So that's not peanuts, it's good money for development. Each little dot that you see here on the map of the US is what we call an advanced nuclear project. One of these advanced reactors, either a microreactor or a small modular reactor, it's a development project there. Now, 70 is a big number, and I will tell you, maybe a dozen of these are credible. The other is BS, okay? What I mean by that is either the companies behind some of these projects are not really capable, they don't have financial solidity, if you will, support, but a few of these are very serious and very capable. So if even half of them or even a quarter of a dozen, say 3 or 4 of these projects actually successful, then that's going to be new because they're not government-driven. They are private industry-driven. So that's all good. So what are some of these projects, the more credible ones? Well, there is one in Darlington on Lake Ontario. This is in Canada, actually. That they're building one of those SMRs, small modular reactors, 300 megawatts. And that should come online in 2029. We'll see. I already mentioned the TerraPower, that's Bill Gates' company, in Wyoming, 2030. That's actually replacing a coal plant. So that's beautiful, right? So coal out, nuclear in, you get, you know, you take out the emissions. X Energy, 4 100 megawatt reactors at the Dow Chemical site. So a nuclear reactor is a heat source, right? You guys got that from the previous description. Fission gives you heat. So if you're interested in electricity, you got to go through that power cycle that we discussed. But if you're interested in heat, you can sell heat directly from the reactor to a customer. Dow Chemical, as a big chemical plant in Texas, they mostly require heat. And so the point of this project is to basically sell heat to that plant and decarbonize the production of chemicals. It's pretty exciting. And then finally, you see these microreactors. Those are actually on a shorter schedule because it's so much easier to make them and test them. And it doesn't entail multi-billion-dollar investments and things like that. So you see here 2026, 2027, et cetera. And this is the last slide, I promise. So a lot has happened in the past 4 years. You know, if I given this presentation 10 years ago, the tone would not be so upbeat. But so much has happened in the past few years. All of which has been, at least for nuclear, positive. Now, obviously, the invasion of Ukraine is not positive. But what has happened with the invasion of Ukraine is that a lot of countries have realized how important it is to be energy independent, to the extent possible. It's impossible to be 100% independent, but try to reduce the amount of imports. And nuclear can do that because once you've bought the fuel, if you understand the basics, you have basically power for many years, okay? So it doesn't keep you sort of on that umbilical cord or supply chain that is required elsewhere. How about climate? Well, climate has been the big game changer for nuclear, big time. Okay, now all of a sudden we want energy that is low carbon, doesn't emit CO2. Well, you know what the COP is? COP, like Conference of the Parties. These are these big gatherings of government, industry, NGOs, et cetera, academia. They meet every year, usually in locations that are very pleasant. Maybe they should come to Santo Domingo. But COP28 was in Dubai, for example, okay? Now, for the longest time, now the 29th is coming up now. For the longest time, nuclear was completely ignored in these meetings, like an outcast. Well, the past 3 editions, nuclear was front and center. In fact, at COP28, like 24 countries, including the US, all the major European countries, et cetera, pledged to triple their nuclear energy capacity between now and 2040 as a way to help with climate change. So the inclusion of nuclear in climate policy has been a very big deal. This is what I just mentioned. Okay, the second largest economy in the world is China. Soon will be the first, by the way. They have 150 gigawatts expansion of nuclear. 150 gigawatts, 150,000 megawatts. Okay? That's, by far, is going to be the largest nuclear reactor park in the world. And they're building it, they're doing it. So it says 15 years there. That was announced roughly 5 years ago. So they're now 5 years into it, and they're on a pace to actually complete this. The United States at the moment has 100 gigawatts of nuclear capacity. So when they're done with this, they'll blow past us. Okay, so China is the leader in nuclear at the moment. A couple of countries that had relied on nuclear for a long time, South Korea and Sweden. At one point after the accident at Fukushima, they decided they want to phase out nuclear. Well, the past couple of years, they had elections that brought in new coalitions, new governments, said, we're keeping our nuclear plants. In fact, we're building more. Okay, so this is very important for us, Sweden and South Korea, because they're big players in nuclear. Even Japan, in spite of the accident, they want to restart the nuclear power plants that have been idle for a while and potentially build more. But in Japan, it's a really, really tough environment for nuclear. Inflation Reduction Act, that's a piece of legislation that the Biden administration passed a couple of years ago, which had a ton, hundreds of billions of dollars of subsidies for clean energy technologies, and nuclear, wind, and solar were all put on the same level. So that's good news. That means the government recognizing the value of nuclear. We already mentioned a few nuclear build projects launched in the US and Canada. I mentioned the Dow Chemical, and so on. So the question I have for you, and this is a presentation I gave yesterday at a big electric reform forum, is will the Dominican Republic join in, or at least consider? I think the time is now to at least start the conversation. And I know that some people here in the room are actively working towards that. So with that, I stop, and let's see if there are any last questions here. Yes?
If we go through it, let's say we have we have a small generator. Yesterday when you gave us this presentation, some guys, we were talking about having this here, and it's like, it's dangerous, we are not still prepared for it. Maybe discipline, this needs a lot of engineering and safety stuff. So if we go through it, what would be like the 3 or 4 key elements for safety that we should care of?
Yeah, that's a good question. So it's not like you snap your fingers and tomorrow you're going to have a nuclear power plant, okay? So it's a journey. The International Atomic Energy Agency, IAEA, again, it's a UN, United Nations agency, as a template for countries that want to become nuclear, right? That they want basically a nuclear energy program. And the template has multiple steps. And depending on, your initial condition, shall we say, to use a mathematical term, it can take between 10 and 15 years from the time that the decision is made to launch a nuclear energy program to the time you have your first production of nuclear electricity. Okay? There are examples 10 years, other examples 15 years, but that's the typical time. So now, getting to your question. Safety-wise, there are a couple of things that the IAEA will demand you do. First, you have to set up an independent nuclear regulatory agency. So this is a government agency that is separate from the nuclear industry that will regulate the nuclear industry in your country. Okay? Now, you already have a nuclear regulatory agency because the DR does not have nuclear power plants, but the DR uses nuclear technology all the time, right? In medical applications, in drilling, mining, et cetera, et cetera. So there already is an agency. That agency obviously does not have the competence now to regulate nuclear power plants. So the first step would be that agency has to be grown, beefed up. The second point is safety culture in operations. That's the question that I think you or somebody else were asking me earlier on, or you were asking me. Again, it's not snap your fingers and make it happen. It's also not, okay, we've been operating natural gas and coal plants, and therefore I'm simply going to pick the operators from there and putting them to work at a nuclear plant. It doesn't work that way, not only because, of course, the technology is different, so they need to learn what the nuclear plant looks like, but also the culture and the attention to details is different. Nuclear plants or nuclear safety culture demands basically the operators to be very, very rigorously trained. There is relentless attention to detail. There is also relentless maintenance that is done on plants to a level that is extraordinarily higher than coal plants. I've visited many coal plants, and sometimes you see, steam leaks here and there, no problem. The floors are dirty, there is clatter, etc. You go to a nuclear power plant, it's almost like entering a five-star restaurant. You could have your lunch on the floor and so on. Everything is spick as pan clean, etc. It's not just the way it looks, it's also the mindset, it's the culture of the operators. They care about their equipment, they care about their plants, and they have to because of the possible consequences of accidents. So instilling that safety culture is very, very important. Now, the good news, you say, okay, maybe that's not part of how things are done here. I don't know. I don't want to, but say that might be an objection. Well, when you decide to build a nuclear power plant, you become part of an international, let's call it club, which is called the World Association of Nuclear Operations. And with the, sort of the membership to that club comes some duties. And duties include the fact that every 2 years your plant will be inspected and peer-reviewed by a team from WANO, that's what it's called, World Association of Nuclear Operations, which will basically expect that you are up to a certain standard in terms of operations, safety, maintenance, and all of that. So there is an international system that ensures that, that basically these plants are operated well. But it all starts, obviously, with the country, with the commitment, the safety agency, and the company that operates the plant's got to be very much committed, obviously, to safety. So I gave you a long answer, though, but it's such an important point. It's not, you don't do this casually. It's a big deal, right? It's a big deal. The latest country that has done it is the United Arab Emirates. They have a lot of financial resources, which I think are higher than the DR, honestly. So they threw a lot of money at it. They were able to import a lot of talent also from abroad. But they started from zero. I mean, they had zero experience with nuclear in 2008 or 2009. And now, 25% of their electricity comes from nuclear. So, and it has for the past couple of years. So spectacular success. And they have, they have, the plant was built by a consortium of South Korean companies. The South Koreans are helping them also in operations. So there is a lot of international cooperation that goes into it. Another country that is entering nuclear, but on the propulsion side, is Australia. More similar to the DR, actually, because they have a nuclear regulatory agency, but it doesn't do reactors. It uses it's for medical applications, industrial applications, and they're now getting into nuclear propulsion for the submarines with the help of the UK and the US. So, any other questions? I know it's been a long session here. Okay. Yes. Well, I don't know if I dwelled on the first slide. I should have said it, what I said yesterday at the forum. Well, I don't need to go back to the first slide, but it's a question. It says, does it make sense for here it is. Does it make sense for the Dominican Republic? I should have said up front, I don't have the answer. You have to find the answer. You have to find the answer. So, but, my job here and yesterday was to just give you the information, some information, of course. There is much more to be learned about this technology so that you can make an informed decision. But, yeah. But yes, it does have a lot of benefits, and it has, of course, also a lot of challenges. So like everything, you got to sort of weigh the pros and cons and then decide if it's the right thing for you. Maybe I'll say one last thing. I don't think I'm revealing anything. Yesterday I was in a private audience with your president, President Luis, and at the presidential palace, and we talk about this, and you know, he's very interested. Obviously, he's not going to tell me, a visitor from MIT, yes, we're doing it or not, but he says, you know, we'll certainly launch a small project to develop a policy that really states, okay, the DR and nuclear, you know, what's our position, et cetera. So this is the time for you guys also to get involved, I think, if if this piques your curiosity. Okay, so with that, yes, yeah, one more.
And on that same note that you were talking about, how can INTEC accompany the government on this journey? Like what, as a university, academic side,
I'm so glad you asked, but that's the simplest question I got all day, right? So I also come from a university. So we talked a lot about the technology. We maybe talked a little bit about culture, et cetera. But you know, what makes all of this happen is people, right? I mean, you got people that are competent, trained, passionate. So there you have the answer, right? INTEC, MIT, I mean, this is what we're here for, right? Inspire the students, educate them, give them the means to then go out there and do wonderful things in nuclear or wherever else they're interested in. So yeah, so big role, of course. You know, a program would take, honestly, would take thousands of people, right? Not just operating the plant, but the safety agency and financing. But the whole enterprise would require thousands of people. One thing that maybe I haven't commented on, but it's important, the economic footprint of nuclear is also pretty high and pretty good. A reason why the folks that live near nuclear power plants actually are very supportive is not just that they're comfortable with the technology, as I said, but it's also they get very well-paid jobs, well above average, even within technical disciplines. So nuclear engineers or nuclear workers tend to be better paid. And they get a lot of local taxes. You know, the plant pays a lot of local taxes, which then are used for hospitals, roads, schools, whatever it is. So this is, you know, it's not just a power plant, it's also a way to stimulate economic activity and all of that. And with that, I think we can close here. So I hope you enjoyed it, and if you have any questions, I'll still be here for a few minutes so that you can ask. So, back to you.
Bueno, se merece un aplauso porque nos dio un 2x1 al final. 2 conferencias. Queremos agradecerles por habernos acompañado, sobre todo al profesor Jacopo Buongiorno por su tiempo, su esmero y compartir sus conocimientos, no solamente hoy con nuestros estudiantes, sino también desde ayer en el foro que se estuvo realizando. Estudiantes, si quieren seguir ampliando sobre este tema en específico, pueden entrar al canal de YouTube del INTEC y ahí está colgado el foro entre la ADIA y el INTEC sobre la reforma del sector energético, del sector eléctrico, más bien. Y nada, eso ha sido todo por hoy. Agradecer, como siempre, su disposición, el tiempo con nosotros, al decano del área de ingenierías por esta iniciativa, también al señor Manuel Cabral, vicepresidente ejecutivo de la ADIA, por habernos acompañado y estar en representación de la institución. Así que desearles a todos un feliz día y que sigan conociendo más y ampliando más sobre el tema, y ustedes ya saben, pónganse a trabajar en eso para que ganen más. Feliz día.
Was he useful? I think he was useful, right?